In physics, gravity, from Latin gravitas, weight, is a fundamental interaction which causes mutual attraction between all things that have mass. Gravity is, by far, the weakest of the four fundamental interactions, approximately 1038 times weaker than the strong interaction, 1036 times weaker than the electromagnetic force and 1029 times weaker than the weak interaction. As a result, it has no significant influence at the level of subatomic particles. However, gravity is the most significant interaction between objects at the macroscopic scale, and it determines the motion of planets, stars, galaxies, and even light. On Earth, gravity gives weight to physical objects, and the Moon's gravity is responsible for sublunar tides in the oceans. The corresponding antipodal tide is caused by the inertia of the Earth and Moon orbiting one another. Gravity also has many important biological functions, helping to guide the growth of plants through the process of gravitropism and influencing the circulation of fluids in multicellular organisms. Investigation into the effects of weightlessness has shown that gravity may play a role in immune system function and cell differentiation within the human body. The gravitational attraction between the original gaseous matter in the universe caused it to coalesce and form stars which eventually condensed into galaxies, so gravity is responsible for many of the large-scale structures in the universe. Gravity has an infinite range, although its effects become weaker as objects get farther away. Gravity is most accurately described by the general theory of relativity, proposed by Albert Einstein in 1915, which describes gravity not as a force, but as the curvature of spacetime, caused by the uneven distribution of mass, and causing masses to move along geodesic lines. The most extreme example of this curvature of spacetime is a black hole, from which nothing, not even light, can escape once past the black hole's event horizon. However, for most applications, gravity is well approximated by Newton's law of universal gravitation, which describes gravity as a force causing any two bodies to be attracted toward each other, with magnitude proportional to the product of their masses and inversely proportional to the square of the distance between them. 1, 2, 2 display style f equals g frac m underscore 1 m underscore 2 r caret 2 comma, where f is the force, m1 and m2 are the masses of the objects interacting, r is the distance between the centers of the masses, and g is the gravitational constant. Current models of particle physics imply that the earliest instance of gravity in the universe, possibly in the form of quantum gravity, supergravity, or a gravitational singularity, along with ordinary space and time, developed during the Planck epoch, up to 10 to 43 seconds after the birth of the universe, possibly from a primeval state, such as a false vacuum, quantum vacuum or virtual particle, in a currently unknown manner. Scientists are currently working to develop a theory of gravity consistent with quantum mechanics, a quantum gravity theory, which would allow gravity to be united in a common mathematical framework, a theory of everything, with the other three fundamental interactions of physics. Definitions. Gravitation is the mutual attraction between all masses in the universe, also known as gravitational attraction. Gravity is the gravitational attraction at the surface of a planet or other celestial body. 6. History. Main article, History of Gravitational Theory. Ancient world. The nature and mechanism of gravity was explored by a wide range of ancient scholars. In Greece, Aristotle believed that objects fell towards the Earth because the Earth was the center of the universe and attracted all of the mass in the universe towards it. He also thought that the speed of a falling object should increase with its weight, a conclusion which was later shown to be false. 7. While Aristotle's view was widely accepted throughout ancient Greece, there were other thinkers such as Plutarch who correctly predicted that the attraction of gravity was not unique to the Earth. 8. Although he didn't understand gravity as a force, the ancient Greek philosopher Archimedes discovered the center of gravity of a triangle. 9. He also postulated that if two equal weights did not have the same center of gravity, the center of gravity of the two weights together would be in the middle of the line that joins their centers of gravity. 10. 2 centuries later, the Roman engineer and architect Vitruvius contended in his De Architectura that gravity is not dependent on a substance's weight but rather on its nature. 11. In the 6th century CE, the Byzantine Alexandrian scholar John Philoponus proposed the theory of impetus, which modifies Aristotle's theory that continuation of motion depends on continued action of a force by incorporating a causative force which diminishes over time. In India in the 7th century CE, Brahmagupta proposed the idea that gravity is an attractive force which draws objects to the earth and used the term Gurutvakara to describe it. 12, 13, 14. In the ancient Middle East, gravity was a topic of fierce debate. The Persian intellectual al-Biruni believed that the force of gravity was not unique to the earth, and he correctly assumed that other heavenly bodies should exert a gravitational attraction as well. 15. In contrast, Al-Khazini held the same position as Aristotle that all matter in the universe is attracted to the center of the earth. 16. Like and subscribe for more. Share your friends.